of any kind, no matter what you might think the limit is going to lead to, we should at least always check direct substitution. And if you do essentially plug the pi in the two places, using good notation, what do you get? Yeah, because on the top, don't the limits just match? You don't really have to go beyond that. The limits match, so the integral is going to have a value of 0. And down below, of course, pi minus pi is just 0. And so you end up with that 0 over 0 indeterminate form, being careful not to misuse the equal sign. We're going to go ahead and use L'Hopital's rule. So with L'Hopital's rule, of course, we do the derivative of the top and the derivative of the bottom. The derivative of the bottom is super easy. Of course, it's just 1. But what skill is used in the top? FTC2, right? You're doing ddx of some integral, and so the x gets just to drop down in, and the derivative and the integral cancel each other out. Take care here that you recognize you do need to multiply by the derivative of what you plugged in, but in this case, that's just a 1. Okay, so then anytime you use L'Hopital's rule, we should retry our limit. So this time you attempt to evaluate the limit. It's going to work out, so I'll put an equal sign, and the answer is cosine of pi is -1 over 1 is -1. Okay. That moment of like, I think I've got it, but now that you ask me, I'm not as sure. Okay, is that good? Okay, fantastic. Why don't you guys try example number 5 by yourselves if you haven't already looked at that, and we'll check your answer here in just a second. Try to evaluate it. Did you guys get an indeterminate form right away? So 0 over 0. Okay, so then we're going to try to use L'Hopital's rule. And when you use L'Hopital's rule, you get, so let's see here, 3x squared minus 4x over 2 over pi. No, what am I doing? I'm integrating. How about pi over 2? Pi over 2 times negative sine of pi over 2x. Okay, so this time when you attempt to evaluate, what happens? You don't get 0 over 0 anymore, do you? -1 over, sure, negative pi over 2. And of course you could simplify that to be 2 over pi? Yeah. If you want. Okay, so L'Hopital's rule. Is there one more? Is that it? That's it. Okay, good deal. All right, do you guys have any questions from L'Hopital's rule? Okay, fair enough. New stuff in Chapter 8, 8.8. We will definitely not be finishing this today. We'll finish this over the next little bit. One word of maybe forethought here. Definitely not going to happen today. Probably won't happen next time either, but we'll see. Chapter 6 is up next, so maybe print those off at some point, throw them in your bag, be ready. We'll just see if and when we get there. I don't know that it'll be this week, but it's conceivable. Possibly we could on Wednesday, maybe? I don't know. Probably not. Just be ready. Okay, so improper integrals. Of course, there's all kinds of jokes here. Improper integrals are not like rude integrals or integrals that don't know social norms, right? There is a very specific meaning here. And the very specific meaning here is that an improper integral is a definite integral where you got infinity for a limit, or maybe perhaps both limits on the integral are infinity, or there's some sort of an infinite discontinuity within the interval that you're integrating. Okay, like a vertical asymptote. Make sense? This brings up all kinds of issues. We'll look at some graphs here. So these improper integrals are very useful. Believe it or not, look at the second sentence. To me, the second sentence is kind of amazing. It says an improper integral allows us to find the area under a curve over an infinite domain, an infinite range, or perhaps even both. Think about what I just said there. You can find area over an infinite domain. there's going to be some contradictions and some, what's the right word? Some paradoxes that you will have a hard time believing, but the math will tell you what it tells you. Okay. Sometimes you'll actually get an answer. Sometimes you won't. Essentially what those next two are talking about. And then the idea here, sometimes recognizing these is very, very easy. You look at them and one or both of the limits is infinity and you're like, oh, it's an improper integral. It's like very easy to see those. What's harder to see is when it's an improper integral because there's an infinite discontinuity somewhere in the middle. You'll have to actually look at the integral and be like, look, there'd be a vertical asymptote at x equals 5 and 5 is within my interval. That makes sense? I'll show you some graphs here and we'll talk about it. So check these out. Here would be a classic case of an improper integral. Like let's say you had, I don't know, some function y equals 1 over x squared. There we go. And so if we have y equals 1 over x squared, that looks like this. And let's talk about how this could be improper. So if you had an integral, and it looked like this, integral from -1 to 1, and we're going to call this f of x dx. This would be a little bit less than obvious, right? Because you'd look at this right here, you'd say, okay, integral from -1 to 1, that's super easy. I've done a million of these, no big deal. But then you look at f of x and you're like, oh my gosh, at x equals 0, there's a vertical asymptote. Duh, I don't know what to do with that, right? And it's right in the middle of my interval. So how am I supposed to integrate where there's this big old gappy thing in the middle, right? It's like this weird, have you ever thought about this, right? Like how are you supposed to integrate over a vertical asymptote containing interval? I mean, it's potentially a little confusing. So that would be one situation where you could have, you consider this to be an improper integral. Here's another one. You could have integral from, say, 2 to infinity. This one, of course, is a lot more obvious because you can see that one of the, well, you can't see my integral. Sorry, somehow that's off the screen, but you can imagine it being there. You've got infinity for one of your limits, right? That's an obvious telltale sign that you have what's called an improper integral. Make sense? And then, of course, you could have something like this, integral from 0 to 3 of f of x dx. Did it show up that time? Almost. Why is that improper?
Because 0 is not defined.
Yeah. You get a vertical asymptote at 0. So not only do you have an improper integral if there's a vertical asymptote right smack in the middle of your interval or somewhere in between in your interval, but if one of the limits kind of butts up against an infinite discontinuity, that also creates this improper integral situation. I mean, think about this. I mean, like if you think about, say, integral from 2 to infinity. So we're talking essentially about this area right here. We know from experience that graph will never touch the x-axis, right? Never touch it. It'll get closer and closer and closer and closer and closer. You know from your pre-calc classes, right? The horizontal asymptote idea. It'll just get closer and closer, 1 over a million, 1 over a billion, 1 over a trillion, whatever it is, but it'll never actually touch 0. So then the question is, how on earth could that integral be anything other than infinity? You see what I'm saying? Since that graph never touches the x-axis, how could you not say the answer is, how could you possibly say the answer is 5 or something like that? Wouldn't the answer have to be infinity? We'll dive into that. We'll talk about where it's a real number, or like under what conditions it would be a real number and under what conditions it wouldn't be, and why. Make sense? You could look at other graphs, other examples here. Here is, and this is going to look very similar. But you could have something like this, g of x is equal to 1 over x plus 3, maybe. So it's a rational function with a vertical asymptote where? Negative 3, yeah, so you'd have this vertical asymptote here. And I think it would do something like this. Or, oops, that right there. Whoa, that's one of my better, actually looks okay. So let me give you some examples here. If you had the following integrals, say integral from 0 to 2 of g of x dx, is that improper? It's not. Because if you look at the interval from 0 to 2, at the 0 and the 2, there are no infinite discontinuities, like vertical asymptotes. And then you look between 0 and 2, and there are no vertical asymptotes in there either. And neither of the limits is infinity. So integral from 0 to 2 would just be your regular old integral that you've done 1,000 times. You'd be done with it in 3 minutes, and 99% of the time you get it right. Hopefully 100% of the time. Make sense? So that is not improper. An example of an improper integral would be integral from, I don't know, say -1 to infinity of g of x dx. Pretty obvious one because one of the limits is infinite. Can you guys think of another example of an improper integral we could get from that blue graph?
-3 to -infinity.
Maybe the other way around, -infinity to -3. Yeah, sure. Integral from -infinity to -3. Now this is kind of interesting because if you look at this, isn't this like a doubly improper integral? Because not only is one of the limits -infinity, which automatically makes it improper, but the -3 butts up against an infinite discontinuity. So you got two kind of different things going on here that you'd have to deal with. This would definitely be a challenging one. In fact, I would split this up into two. It's because you got two different behaviors going on. One of them is off to the way far to the left, and one of them butts up against an infinite discontinuity. This would probably be something I probably wouldn't test you on for time's sake, because this would take you a long time. You'd have to do two separate questions and then add the answers together. Certainly doable, but it would take a while. You're right. That's very incredibly improper. Anybody else have an improper integral you could construct?
Would
If you-
-4 to -2 be one?
Yeah, definitely. Integral from -4 to -2. What's the reasoning on that?
Because it doesn't exist at -3.
Yeah, get the vertical asymptote. It's not that g of x doesn't exist there, because you could have a hole there, right? You could have a removable discontinuity, and we wouldn't have to deal with it in the same way we would deal with this. It's specifically the vertical asymptote behavior. And you think about Caroline's idea for a second. When you think about like the idea of area, you think, all right, same idea, we're going from -4 to -2. We think about this, that would essentially be this area and this area right there. And as you guys know, with the vertical asymptote, the graph here and the graph there will get closer and closer to the vertical asymptote, but never touch, never cross. So how could the answer possibly not be infinity? Right? If you think about it, the graph's just going to get closer and closer and closer, and you're just going to keep going, like when you think about area, wouldn't you just keep going plus a little bit more, plus a little bit more, plus a little bit more? How could that plus a little bit more not lead us to infinity every single time? Does that make sense?
I do have a question about that one.
Yeah.
Is it possible for that to be 0?
Mm.
Because
The area
it's a
being,
equal positive negative area.
yeah, it's possible. Depends on the behavior of the graph. But yeah, it's possible. Okay. Any other questions? The goal of this little portion of the notes is, do you understand what an improper integral is? We haven't talked about what to do with it yet, but do you understand what it is, where it comes from, those kinds of things? Please ask if there's, this is new for everybody, so please ask if there's anything that you're a little unsure of. Okay, fair enough. Well, let's do a couple of examples. Let's take a look at, let me make sure yes, this is what I wanted to do. Let's go number one. Example number one, integral from 1 to infinity of 1 over x squared. I must say, we're like when it comes to understanding why these functions do what they do, we'll use some somewhat informal language. If your curiosity is piqued as to some of the more detailed stuff, stuff like that, proofs of these sorts of things like ironclad proofs are covered in what's called a real analysis class. If you ever get an opportunity to take a class called real analysis or intro to analysis or something like that, things like this will be proven in no uncertain terms, right? We'll kind of use some colloquial expressions, easy to understand images, but they're far from proofs. Make sense? All right, so here we go. Integral from 1 to infinity of 1 over x squared. We looked at one of these more or less just a few minutes ago. So I'm gonna just redraw the graph real quick, just for reference. And I'm only going to be concerned about the interval that we're working with. So 1 over x squared, at least on the positive domain, looks something like that. And we are looking at what's happening from 1 to, there we go, infinity. So, more or less, if you wanted to think about this sort of informally, you'd be saying that we're sort of looking for that area. Make sense? So intuitively, it would be very understandably for someone to say, well, you know what? I don't have to show any work at all. I think the answer is going to be infinity. Because won't there just forever, in perpetuity, won't there just be a plus a little bit, plus a little bit, plus a little bit? Right? Okay. So here's how we handle these. You look at this and you see this right here and you say, oh, automatically, oh, come on, there we go. Automatically, because of that infinity, this is an improper integral. You double check the 1 and make sure that the 1 is not part of an infinite discontinuity. And it's not. So it's not one of those doubly improper integrals like Darian was talking about earlier. This is just a regular improper integral. So here's how we would deal with this. Whenever you've got an improper integral, there's something you have to write. I want to be really clear about that. There's no getting around this. You have to write this. If I can write it, it would be fantastic. Lim. These have to be done with limits. Okay? So we're going to go limit, and we're going to say limit as b approaches infinity. And we're going to write it as 1, integral from 1 to b of 1 over x squared dx. So if you got one of these improper integrals, and you can identify obviously one of the limits is infinity, then you're going to say, well, I'm going to make this be the limit as b approaches infinity from 1 to b on the integral of the integrand. Okay? You've got to use limits. And so you have to do that. You absolutely must use limits. That's the only way to deal with infinity, right? It's the only way to deal with an infinite discontinuity. So from here, let's talk about what happens. We would say limit as b goes to infinity. And we're just going to use our regular old antiderivative FTC1 routine that we've done so many times. The antiderivative of x to the negative 2 would be negative x to the negative 1 evaluated from 1 to b. And we'll do FTC1. We'll plug in the b, plug in the 1, and subtract. So this will be the limit as b goes to infinity of negative of b to the negative 1 minus the negative of 1 to the negative 1. Let's clean this up a little bit. Limit as b goes to infinity. This would be negative 1 over b plus 1. Fair enough? Okay, so we did all that calculus stuff, FTC1 with the antiderivatives, and we finally end up with this expression right here, something that's relatively easy to evaluate, right? What's the limit as b goes to infinity of negative 1 over b?
0.
Plus 1? 1. Interesting. So, you stop and think about that for a second. You're like, how on earth could that area be 1? Now, let's talk about a couple things for sure that I want to make sure you understand. Number one, that area that goes off to the right forever and ever and ever, it really never stops, right? It never really stops. We put the limit on there, and remember, the limit is, all this hinges on the idea of the limit, right? The limit is basically, as b gets bigger and bigger and bigger and bigger, what is the pattern of behavior of the the thing that comes next, right? Remember that? It's easy to get hung up and kind of forget what a limit is. A limit is not, when x or when b is infinity, this integral is 1. Remember, that's not what a limit is. The limit is, as b gets huger and huger and huger, the pattern of behavior of that integral's value goes towards 1. So in other words, if you just really felt like punishing yourself and you started just adding up, like doing all these little rectangles, right? Can you imagine this? Can you imagine doing a Riemann sum for this? Right? What if you did a Riemann sum where the subinterval was like 1/1000th, right? And you're just like, okay, first rectangle is 1/1000th wide. Let's find the height. And then you did the second one, the third one, fourth one, fifth one, sixth one, dot, 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 dot. You got to the end of the day and you did like 600 of them. And you're like, yes, I accomplished something today. Not really, but you did a lot of arithmetic for sure, right? Well, if you keep on adding these little itty-bitty Riemann sum rectangles, what you would find is that the pattern of behavior is headed closer and closer and closer to 1. Can I draw a parallel with you guys? Maybe something you had in a pre-calc class? And we'll actually revisit this year for sure. In a pre-calc class, did you guys do geometric series? Surely you did, right? Where, like, to get the next term, you multiply by a common ratio. So let me give you a geometric series. So first of all, what is the common ratio? 1/2, right? Every time to get the next term, I'm multiplying by 1/2, right? 1 times 1/2 gives me 1/2. 1/2 times 1/2 gives me 1/4, et cetera, et cetera, et cetera. Make sense? Okay. And so then this is a series, and so we're adding each successive term onto the previous sum. And so if you start to add this up, let's just informally do this. So obviously 1 plus 1/2 is 3/2. You had 3/2 plus 1/4. 7/4, right? 7/4 plus 1/8 would be 15/8. 15/8 plus 1/16 would be
31.
36. No, wait.
it would be 31 sixteenths. 31 sixteenths. So you think about each time. So we had 3/2. Let's see here. I got to think. 3/2, 5/4, 7/8, 15 sixteenths. No. I'm doing it backwards. 15/8, 31 sixteenths. Are we getting closer and closer to a value? Can't you start to see the pattern emerge? And so if I said, hey, if we added up all the numbers, like if we said plus dot, 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 if we were able to add up every single number in that series, what would you say that we'd be headed towards? 2, right? 31 sixteenths, right? There, if you take off the one, we're headed to 1, right?
Oh, yeah.
Yeah.
I was going, yeah.
Yeah, and so that's another way of looking. Sometimes you start with 1/2, but whatever. And so from an intuitive standpoint, you look at that and you're like, oh, I get it. Yeah, I see how the answer is not going to go above 2, right? Because you're never going to get like just that 1 over the 2 mark. You're always going to be just like 1 under the fractional 2 mark. But it's getting closer and closer and closer to 2. This is the idea that we see here. Like if you were to do those Riemann sums, it would take you forever, but you'd see, well, keep adding up all these little tiny little skinny rectangle areas over and over and over again. I'm never getting over 1, and I can see that I'm just going to butt up against 1, right? Going to get closer and closer and closer to 1, but never actually hit 1. So next time we're actually going to see, well, not next time. Next time we're going to do a quiz, but the time after that, we're going to see an example here where similar looking one. It's example number 2. I'll just let the cat out of the bag here. Example number 2, you're going to find, if you just peek ahead, look at it real quick. Example number 2 looks the same except for
Drop the
one little difference.
Doesn't have squares.
Squared, or not, right? This is to the first power, right? It looks very similar. We're going to find that that one, the answer actually is infinity. The answer doesn't exist. It's what we call diverges. We'll talk about that here in a second. And so just to give you a hint about why, or like I guess I should say more of a pattern than anything else. The pattern is simply this. Here's why that integral we just did gives us 1, yet the one we'll see in number 2 doesn't exist. It has to do with how fast does that graph approach the x-axis. If it approaches it fast enough, you'll get an answer, like 1. If it approaches it too slowly, like the one we'll look at next time, the answer ends up being infinity. Like the rectangles grow just fast enough to head towards infinity. And we'll talk about kind of the dividing line, like where, how we can kind of divide these up into those that will work and those that will not work. And it'll kind of really lead us into some second semester stuff too. So that makes sense? Let's take a look at example number 2, because we have about 5 minutes left, right? Let's do this now. Let's look at this. This will be a good way to finish. I'll throw some different ones at you. Oh man, I love number 3. We'll get to number 3 next time. Number 3 is really, really good. Okay, so example number 2. So with this one, you look at it, and it's, again, this is a really obvious one. Hey, there's an infinity for one of the limits, and it's like, okay, it's a dead giveaway. It's an improper integral. So we always have to start with writing limit. It's the only way to deal with stuff like this. So we're going to write limit. I don't know why we choose the letter b. I know that it's the integral from a to b typically. But even when the lower limit is infinity, or some version that we still write b. I don't know why. You could write a if you want. It really doesn't matter. Limit as b goes to infinity, integral 1 to b of 1 over x dx. So that's the setup you got to use. And then we just proceed with normal, regular old antiderivatives in FTC1. So limit as b goes to infinity of natural log of x evaluated from 1 to b. And then we do FTC1 and do the plug in and subtract thing. So limit as b goes to infinity of ln. I can drop the absolute values, I think, there and there. What's ln of 1? 0. Yep, so we can happily just drop that. So it ends up being limit as b goes to infinity of natural log of b. Okay, so let's think this through. If we're going to do b is getting really huge, ln of b, what happens here is b gets huge. What does ln of b do? You know what might be helpful? Look at a graph of natural log of b. Now this is not the graph of the original, right? So if we just take a quick peek at the graph of natural log of b, doesn't it look something like this? It goes through 1, 0. And we're talking about the limit, we're talking about the limit as b goes to infinity. So we're talking about that behavior. As we go way out to the right, what is natural log doing? It's getting bigger. So is this graph ever going to do this? Nope, it's not. Is it ever going to do this? Nope. Why don't I just continue on its merry little way at an increasing pattern? An increasing pattern it's increasing at a decreasing rate, and so it really wants to not increase anymore, but it'll keep increasing, right? Just very, very slowly. But won't it keep increasing? Yep. So as b gets huge, ln of b will get huge. Yeah. So we would say then, let me get rid of this stuff. Yeah, I know huge is a very technical math word. Huge. It's sorry, I was mispronouncing it. It's huge. There we go. So yeah, infinity or dne, right? Because infinity is not a real number. So if you just want to say dne, that works. Or a new term, which I mentioned a few minutes ago, is the integral diverges. So diverges is a term meaning that the integral's value is infinite, right? You could say that the series is diverging as well. So you'd say that it doesn't exist. And the reasoning being what I mentioned earlier. 1 over x simply does not approach the x-axis fast enough. 1 over x squared does. Later on, you're going to find out that 1 over x cubed, x to the 4th, 1 over x to the 5th, 1 over x to the 10th, 20th, 30th, 40th, 50th, they all do approach fast enough. But as soon as you get to 1 over x to the 1st and numbers below that, it's too slow. You'll always get a diverging integral. Say again? The x-axis. Yep, so and if you think about why that is, as x gets really, really big, if you're squaring it, doesn't it make 1 over x squared get smaller faster than if it was just 1 over x to the 1st? And so if you have 1 over x cubed, that pattern is even more accentuated. 1 over x to the 5th, even more, so on and so forth. Ooh, yes. We actually, we're not going to deal with it. You can actually have an x to the x scenario, but it's not part of our curriculum. So that's one of the things I'm not going to do. So. Okay, that's it. I will see you for your quiz tomorrow. Have a wonderful day. Welcome back.